So welcome to this session. My name is Jens Melhede. I'm from Violin Memory, and together with our good friend Michael Frandsen from Mental Note, we will do this presentation for you. And let's get started. So the agenda, I think Michael will go through that because most of it is his.
Okay, so we're just gonna go through the typical storage challenges that we see on SQL Server. We're gonna run through new components that are available to do basically platforms in a different way, and we're gonna go into how specifically we can design basically a paradigm shift of SQL Server platforms. And as part of that, we'll also touch. I think somewhere in the name of the session it was Windows Server 2012 R2 and SQL Server 2014. Most of what we're going to discuss also applies to Windows Server 2012 and SQL Server 2012. So I think 3/3 or 3/4 of our session will apply to 2012 versions, whereas the last part is the new stuff that are specific to SQL Server 14 and Windows Blue or Windows Server 2012 R2. So, and then we'll also touch a bit upon new stuff coming from Violin Memory.
Sure. Good. So just very briefly on my background, I have worked in the storage business for 10 years. Before that, I was at a customer side working with infrastructure at both Microsoft, Navision, and Egmont. And I specialize in, of course, storage performance, how applications can benefit from flash memory and virtualization infrastructures. And yeah, that's briefly what I do. And Michael? No, that's later, sorry. So let's start with what is Violin Memory. So we are founded in 2005, so we've been doing this for some years. So we are not a startup company, we are a young company. We are approximately 600 employees around the world. And so what we do both tier 1 storage systems, we do flash memory cards, and we do acceleration into the memory fabric. Yeah, we have sold more than 4,500 systems, so we are not a newcomer into this space. Earlier this year, Gartner did some surveys and analysis around the market share from flash storage arrays, and Violin Memory is, maybe to a surprise for somebody, the market leader for this. In front of EMC, IBM, and NetApp. So we are selling a lot of these flash memory arrays to a lot of big companies and mid-sized companies like we typically have in the Nordics. Another survey was done by the InfoPro, where they ask a lot of customers, have they deployed a memory technology, flash memory technology, and what's their plan for starting up deploying memory technologies in the storage space. And looking at these numbers, it's even more visual that we are the market leader with a lot of systems out there running in production for many years. So it's not a new technology. Maybe for some companies it's new, but we have been doing this for many years now. So we saw that we have the number one in the market share by Gartner. We have a lot of benchmarks where other companies, server vendors and infrastructure vendors like VMware and Microsoft have used our technology to make their application, all their servers, all their infrastructure run as fast as possible. Because as most of you probably know, storage is the slowest part of the infrastructure today. CPUs are extremely fast, memory is fast, network is fast, but storage is slow. So we change this game and make all the applications and the infrastructure run extremely much faster. Integration with SQL Server, VMware, SAP, and all the other guys. So SQL Server 2012 and Windows Server 2012 R2 has been developed together with Microsoft. We have made suggestions for them to optimize their kernel to run faster on flash. And Microsoft is a large customer of Violin also. So the data center disruption. we call it the Violin effect, and it's huge numbers, we know, and it can be done. Not in every case, but in a lot of cases, we can reduce the storage footprint by 90% because you don't over-provision any storage anymore. You just run 100% with 100% performance. That means the cooling goes down 90% because you have less equipment in your data center. Servers can reduce by 80%. And that's because a CPU is waiting for storage all the time. So if it's not waiting anymore, it can do more work. So you can do with less servers for the same job, or you can increase the load 2, 3, or 4 times with the same amount of servers. If you reduce the number of servers, you reduce the number of licenses. That's very easy. At the same time, we speed up the transaction 10 times, some cases 20 or 30 times, but let's just say 10 times at transaction acceleration. Okay, that is. So what we have, our portfolio is that we have a single pane of glass to manage all the ways you can deploy Flash. And so one GUI, one pane of glass to manage, for instance, our memory arrays. That's a storage tier 1 array, extremely fast. 1 million IOPS and microsecond latency, manage several of those, several tens or hundreds of those from one pane of glass. Another option is to deploy Flash in the server itself by having PCIe cards. And we took our knowledge around designing a storage system, put that into a card to make extremely fast cards with a very low latency, lower than anybody in the market, and without having any CPU and memory footprint in the server. So very low latency, very low footprint to deploy in the servers. And lastly, we have these memory appliances for customers that are a little reluctant to deploy Flash as a new array, but would like to get the speed out of their existing array. So we can put in these devices into the SAN fabric non-disruptively. No one will know it's happening, it's just running in. And then it accelerates all the reads and nearly removing all reads from an existing storage system that can then be optimized for writes instead. So that's very transparent to get acceleration of an existing investment that many companies have out there supporting fiber channel. So we have a lot of customers and many of them are very large. Our largest customers, AOL, they have nearly 3 petabytes of Violin Flash. So that's nearly 100 systems running Flash. And every time it's a EMC VMAX high-end system goes out of service, they replace it with a Violin array. And they get a ROI within 3 months because they reduced footprint in the data center and reduced power and cooling costs. And we have eBay and a lot of other big companies. So over to Michael.
Yeah, I'll do that pretty quickly. I've been working with Windows since back in 1993, the first version Microsoft ever did. I've been working with SQL Server since 4.21a. I don't know how many of you have been around since that version. And today I'm sitting in advisory boards in Redmond in both the Windows, the Hyper-V and the SQL Server product groups. Currently working with SQL 14. We just released Windows Blue. And on the same time I'm working with the Violin Memory R&D in Silicon Valley. I also have an R&D agreement with the HP in Palo Alto and Fort Collins in Houston, where I sit with upcoming server models. I've done some of the largest reference cases on SQL Server in the world, and when SQL Server Gartner moved that into the leaders quadrant of their Magic Quadrant, they mentioned 3 customer cases. 2 of them were mine, and the last one was based on best practices that I helped HP and Microsoft do. And since they know I go a little into motorsports, I got this interesting trophy as a thank. My company is just a one-person company, no affiliations. I don't sell software, I don't sell hardware, it's just consulting. So but what we're going to talk about today is mostly the storage challenges of SQL Server. I mean, we have many kinds of challenges with storage. Some of them we've solved, most of them we've solved, but in combination we start to see the problem. So if we want fast storage, but we also want shared storage to do clustering, that tends to be a problem. We can easily do fast, we can easily do shared, but it's very difficult to do both unless money is no object. The second thing is that most SAN vendors has this notion that if you just buy a big array, it will be faster. Spend more money and our storage will be faster. The problem is, as most of you probably know, is that the big systems is mainly Unix and mainframe based, and they run Oracle and DB2. But SQL Server is very special because it uses a lot of CPU power trying to convert random I/O to sequential I/O. None of the other big databases does that. And that means as you spend more money on your storage array, either they flatten or they actually start to degrade in performance because of this specific thing that when you buy the really big arrays, they do Oracle or DB2 optimizations, but that means putting in a random pattern algorithm on a sequential stream that really makes a mess out of the I/Os. Then the second problem about storage arrays is typically SQL Server is not the only consumer. We have lots of systems getting data out of it, so the aggregated bandwidth we try to pull out of it is much bigger than what we actually have available. So our batch windows might differentiate because one day we are not doing backup of Exchange, the next day we are doing backup of Exchange, so we lose bandwidth. Back in 2007 I wrote a white paper just after SQL Server 2005 about placing TempDB on local drives in a clustered environment. But the funny thing is that here it should say Mark Sousa. This is a really high up guy in the SQL Server product group, and he came with all these arguments about no, we don't need local stores, we don't need fast, we just need a SAN, lots of cache, and everything will be solved by that. But the funny thing was, last year at the summit I did this talk, and Mark posted this picture of himself just 2 days before the October festival, and I'm guessing a guy that looks like this, who can trust that, right? So we're gonna get back to that. Microsoft also made a big change in that philosophy. So the next problem with storage is that usually when you go to your IT department or your storage vendor and say, well, we're pretty sure from the SQL Server perspective that we're waiting on storage, and they come back with this number saying, well, we're 8% utilized, so we have lots of I/O. But that's usually because they measure the spindles. But on top of the spindles we build logical drives, right? But inside the storage array we have cache lines, we have parity engines, we have port processors, we have ports, we have backplanes, we have SCSI controllers. So what if we are stalled somewhere else? Then we get the fabric, and if we move to the server, I mean, we have so many other things we need to take care of in order to get what we really want in a balanced system is to have all the CPUs at 100%. But that means all of these components need to really work perfectly. Looking at an example from a this is a really large storage array from one of the largest vendors out there, and what you look at here, these are the ports. Down here we have the port processors, these are cache lines, and down here we have the SCSI controllers and backplanes, and each of these boxes is the actual spindles. And as a matter of fact, down here, this array group here is solid state drives. All the other ones are mechanical spindles. The color basically says the utilization, 0 to 10%, and up here we have 100% utilized. And this was the default configuration. Again, usually storage array vendors, present company excluded of course, are pretty arrogant about their arrays and say, well, we are fully automatic, auto-loon, moving, and we will automatically configure rate levels. But this is what we got, almost fully utilized on the port processors, but no activity where we really want it. We want to utilize the drives. Then they went back after their first measurement and said, well, okay, we're going to optimize it for a big database workload, which meant Oracle DB2. So we got this out of it. Now we're 100% utilized up here. Our cache lines, they're maxed out, but we still don't get anything out of our spindles. So we tried to help them a little bit, saying, well, SQL Server is a little bit different. And doing it that way, we actually got what we wanted. All the infrastructure is balanced, but we want the spindles to be fully utilized. But the funny thing is, when you put NAND flash or solid state in a traditional packaging of all these components, we actually didn't see a big improvement, maybe a factor of 3 on the solid state drives compared to the mechanical drives. So getting rid of all this legacy is actually really what we want. So going back to this drawing, well, what if we could get rid of most of these things and say, well, we have some NAND flash, we present a LUN directly to an HBA, and we get rid of all the DSMs and all the software on the servers to get a much more simple solution. And I think that moves it over to you.
Thank you. So just looking at NAND flash or SSD or whatever you call it, they are not just the same. They are implemented very differently. So one of the advantages that we have in Violin Memory is that we are part of this global organization called Toshiba, and they invented NAND flash. And only 2 companies can buy directly from Toshiba. That's Apple. You wonder why? And then it's Violin Memory. Everybody else has to buy it through different tiers and different vendors that needs to make money. So we buy it directly at the factory at a fixed price, and we get access to the engineering around how flash can be optimized and how it works more performant. So we start with the Toshiba flash. And we buy that, of course, to a very good price. And then we put together these flashes in our cards called a VIM, Violin Intelligent Memory Module. It looks like a small server. It has a CPU, it has DRAM, and NAND flash, and it runs our own operating system optimized for getting the most out of flash. Those cards are put together with our V-RAID patented technology, RAID technology that acknowledge the strong sides of flash and the weak side of flash. And they are packaged together in 5. And then it's packaged into big arrays, and you can put several ones in a rack. So that's how we build the flash arrays. So comparing to traditional or everybody else architectures, so we are built from the ground up to use flash. So we are not built in the 80s or the 90s. We was built from 2005 and onwards. That means we could use the new technologies available to get much more speed. So we are engineered for flash. We're not engineered for disk. And we get what we call memory-like performance. We had the SAS Institute that did a test on our array, and they came back and said, you are 2 things. You are the infinite memory module, because we are nearly as close as an in-memory database in their environment, or you could call us slow DRAM. Don't want to be called slow, but that's what they said. But compared to DRAM, not bad. So our latency is measured in microseconds, not milliseconds. And remember, a CPU is running in nanoseconds. So it's much closer to DRAM, much closer to the CPU load. And we have what we call distributed I/O. That means we distribute I/O of all the modules and all the arrays we have. Not having single point of congestion in one area on one disk, but making sure we're using all 8,000 NAND flash in a system to get a parallel performance. Compared to everybody else is latency in milliseconds and non-distributed I/O. So looking at the hardware very briefly, it's made to be hot swap anything. So there's at least 2 of every component, and you have no downtime upgrading or changing any component. But remember, the only mechanical thing is the fans. Everything else is silicon. So the rate of error is quite low. We had an internal calculation that said something like nearly 600 years between failures. And that's because of the silicon. So a little education in what is flash good for, what is not good for. So flash is very good at doing reads. But then there's a problem. You cannot overwrite data in flash. You have to clean up first, do erases, and then you can do writes. That process is called garbage collection. Everybody has to do it inside the flash system. This is in the beginning, and very quickly after a week or 2, this is the situation. So the erase process plus the write process takes around 9 milliseconds. So if you've ever tested flash and did a lot of writes to it, you have seen this behavior. It is very slow at doing writes, or at least the latency will go up like a heartbeat. Sometimes it's very, very slow because this process is happening in the background. It's much slower than a 15K device. So that's the challenge. So what we have done, we just built this PowerPoint and it's fixed. Very easy. No, of course, we have to do the arrays. It's the nature of flash. But we do it intelligently in our RAID technology. I'll get back to that. And
maybe that's the right cliff, if somebody has heard about that.
Yeah, this is to take care of the right cliff. I think I'm going to show a picture of that. But also look at the writes. We accelerate the write from 900 microseconds down to 500, nearly twice as fast natively writing to flash. And that's due to the relationship with Toshiba, where we sit together with engineers, have access to that. Nobody else has that. So we can accelerate performance even further than the native is able to do. So this is our Vim, our capacity and performance module. And I already talked about it. It has CPU, DRAM, and flash. And we are called Violin Memory because we use both flash and memory to do our performance. We're not only reliant on NAND flash, because as you saw, for write it's not that fast, but DRAM, as used for a buffer for writing, is very, very fast. So we combine those two things together to get extreme fast performance. We're actually faster on writes than on reads on latency. So this is how we do write optimization. So let's say a 4K block comes into the array. It's split into 4 1K blocks, the red ones down there. Is there a pointer? No, down here. And 1 parity. Yeah, okay, good. So we just split the write and acknowledge in DRAM, and we're done. That's extremely fast, much faster than writing to flash. And we make sure that we always have available capacity to write to. So that's the acceleration of the write process. So we have to do the erases sometimes. So what we do there is that each module, 5 modules, are talking to a V-rate controller up here. And one module says, now I need to do the housekeeping process. So it can dynamically jump out, do housekeeping, move back again. And it's all coordinated by the rate controllers up here. So that means in this case, this rate group can still be used for reads, because these four blocks can be rebuilt with the V-rate controller in nanoseconds. That's even faster than reading from flash and then presented. In a traditional SSD, if an SSD is busy doing this housekeeping, it will block any reads, block any writes. So it's not only a write problem, it's also a read problem when this process is going on. And then the next module down here is available for both reads and writes, and this one is available for read. And we have, in our arrays, we have 4 of these sections. So we can keep on writing for hours and hours with full bandwidth. So this is what it really means. This is the important slide. So today, in a traditional environment, your CPU is working, that's the green part, very good. Then it's doing I/O wait. If this is in milliseconds and this is in nanoseconds, that's 1 million times slower than the CPU. So it's idle, waiting for the process to finish writing, finish reading. Then it can move again, and then it has to wait. But if these wait times are at microseconds like it is on a Violin array, you get very efficient CPUs. And that means lower number of servers and lower number of cores, or you can increase the load with the same amount of hardware you have. So this is a test we did for one of the biggest banks in the world that had 32 blade servers running virtualized Oracle. They wanted to increase the utilization and lower the cost of licensing for Oracle. So in this case, they could only run around 20% on the CPU utilization. The rest of the time is waiting for I/O. Then they moved the same load to a single blade with 8 blade servers, and now they could move the bar on the CPU to around 80% and get the same load done on 1/4 of the CPUs that was previously used. So this is what you can do if you have very, very, very fast latency. So is it just a story I'm telling, or is some independent test of this? This is the closest independent test we could find. This link down here, Storage Review did some tests on some Fusion cards and some SSD cards where you see latency. It's measured in milliseconds. And in the beginning, they are all quite good. They are around 4 or 5 milliseconds. Not very fast compared to a disk, but still okay. But then this happens. Latency goes up here. And this is an average database load, 70% read, 30% write. You see latency, some of them are peaking above 100 milliseconds. And that's not very good. So you need a very low sustained latency. We are measured in microseconds, not milliseconds. Together with Fujitsu, we have built this solution called a fast track. You probably know about it. So it's a predefined solution where we have 3 different ones. We have a 20 terabyte, a 60 terabyte, and according to what I've been told, the largest in the world, 240 terabyte fast track solution, certified, ready to go. And we have reference architectures of how it's been done. So some of the business impacts, because we are probably all of us technicians, but the ones that pay for this is the upper management. They want to see results in savings or better earnings, one or the other. So we did some billing with monthly billing runs that went from 72 hours down to 22 hours. That meant they did a lot of extra bottom line on that company because they could do it this fast. A supply chain management went from 7 hours to 2 hours, and telco order handling system is a remedy system, did a 9x improvement. So you get the picture. If latency is this fast, the application will run much, much faster. This is the system, the store system that we have. We have, I'm going to talk about all of them, but a 3U box can have up to 40.4 real terabyte usable and deliver 750,000 IOPS and nearly 4 gigabyte of throughput. So that's a very low footprint to deliver a lot of performance. And come and talk to us on the booth to get more information. So can it really be at microsecond numbers? So this is a test I did for a POC in our labs in the UK, where you see measured on our array side, you see these latencies, 253 microseconds. That's for read, and the write performance on the same load was 90 microseconds. Compare that to your current storage environment. So this is probably 50 to 60, maybe 100 times faster than that. Was it a small load? No, it was 1 gig a second, 260,000 4K IOPS. So this is extreme performance. And you saw before what it can do for the application side. Very shortly on PCIe cards, because we started with our arrays, then moved in May to PCIe cards. And very briefly, what it does is that it delivers the same technology in a card, of course at a much lower price. We use the same rate technology to get very sustained, very low latency, and we don't use host footprint, so no CPU or memory is used on the server to run this. So this is the next generation of hardware optimized PCIe cards. And the specs, you'll get the presentation afterwards, so you can see how big are they, what are the kind of performance you can get with these cards. So what we're all about in a CEO slide is this. We're about time, we're about money. So either you need time back, you get to know to do more at the same time, or you need to reduce your costs. And we can do both with having this extreme amount of performance. And then it's back to the technology around infrastructure.
Okay, so how do we connect storage? Usually we've done it with Fiber Channel, but Fiber Channel has been stuck at 8 gigabit a second for many years. I know 16 gigabit is out there. I'm guessing no one in here is using 16 gigabit Fiber Channel. I mean, at least I have no customer who does it. It's very expensive. Then we have iSCSI. iSCSI came from the lower ground with 1 gigabit, moved up to 10 gigabit, but usually we don't have enough links. So on a 10 gigabit iSCSI array, maybe I have 4 or maybe 8 links. But on my Fiber Channel side, I can do maybe 80 8 gigabit fibers. And then we have the NAS, I mean network attached storage, and I'm guessing none of you would probably put your SQL Server transaction log on a network attached storage device. I mean, and trying to find some examples of why I wouldn't put my SQL Server things on a file share is something like this. I'm guessing most of you have experienced just copying a file from one place to another, and in the middle it suddenly says network name no longer exists. And while finding screenshots of those errors, I found out, you know, platforms that do not fault apparently also has problems. It's just not just a Windows issue. But maybe there's a reason it's so unstable. The SMB protocol has over 100 commands, and I don't know if you can think of 100 things to do with a file share. I mean, you can create a file, you can delete a file, you can read it, you can modify it. I mean, it's crazy, and it even had 14 distinct write commands. I mean, just think about being a developer and need to write something to a file share. Which one of the 14 commands should I choose? So Microsoft basically cleaned it up in version 2. They added performance in 2.1, except that performance was not enabled by default, and the applications needed to support it. On the SQL Server side, well, before 2008, file shares was not supported. You could enable it with a trace flag, but if you called Microsoft support, you would not get any help. 2008 R2, now you could put user databases on file shares, but still not system databases, and also it could be used for high availability scenarios. So two things happened: SQL Server 2012 and Windows 2012. From the SQL Server perspective, well, now everything can be placed on a UNC path. So system databases, transaction logs, but you can even use UNC paths as storage for a clustered SQL Server instance. So I no longer need block level storage locally to my SQL servers. And then I met Mark Suse last year, and that feature that would tend to be local on a cluster node, going from I'm an idiot to, well, great suggestion. So Americans do wake up and figure out that we need performance, and a storage array, a traditional storage array, was not the way. But and even in the Violin space and in the new space, if we can offload something, if you really need performance to our transaction log, well, why not put tempdb on something local, on PCIe cards, so that we will offload our shared bandwidth. So with Windows Server, we really brought in something new. First of all, InfiniBand, and I'll get back to that. We now have NIC teaming. I don't know if you ever realized it, but when you team two network cards to do one virtual network card, so if one link fails, it will still be connected. That was not something Microsoft ever supported or ever built. That was something either server vendors or network card vendors built. And in many situations, you could not get support. If you were an HP customer, HP took to the course of building their own network teaming software. So if you had Broadcom, Intel and Mellanox in the same box, one software would be able to team across them. If you're an IBM customer, they didn't. So you would need to install Broadcom's virtual network driver, Intel's virtual network driver, Emulex's virtual network driver, and so on. And just imagine the conflicts of that. Now all of that is built in. Then the last thing is SMB 3.0. The version previous to this was 2.1, and during all the betas of the Win 8 kernel, it was called SMB 2.2 Plus. But just a few weeks before release, marketing thought that, well, from 2.1 to 2.2 Plus really wasn't that sexy of a jump, so all of a sudden it was SMB 3. But it brought some new things also that we're gonna get into. But going back to InfiniBand. InfiniBand is an old technology. It's 12 years old. It's been used mainly in HPC, high performance computing scenarios. Microsoft embraced it only in that specific version of Windows for HPC. But with Windows 2012, you can plug it in. It works like a normal network card. You give it an IP address and you're done. There's nothing special about it. But InfiniBand has massive throughput. It has really, really low latency, and we just discussed a lot about that. And it is RDMA capable, and I'll get back to what RDMA is. So looking at the throughput, InfiniBand works a little bit like PCIe slots. So you can get an X1, an X4, an X8, X16. We do the same here, X4, X12, X8. And then depending on the version of InfiniBand we're running, currently we're using FDR, which is 14 gigabit, and then X4 editions. So FDR on X4 is 56 gigabit per second, but that means 6.8 gigabytes per second per port. That's a lot of bandwidth. So actually our biggest problem is no longer our interconnect as it would be on Fibre Channel iSCSI. Our biggest problem is that the PCI slots out there is fixed at 3 gigabytes a second on older servers. But just imagine that you went from a really big problem of getting more performance to your storage to your max throughput on your PCI slot is actually now your bottleneck. And we can do something about that. Buy a current generation server with PCI Gen 3 and we don't have that problem. But that means a port, an InfiniBand card with 2 ports moves 13 gigabytes a second on one card. I think that'll probably be more than any of you have on any of your servers currently. And another good thing is that, I don't know if you know, but normal networking, let's say iSCSI, that moves 1500 bytes in its default configuration. And if we look at 1500 bytes, that's somewhere around here, that's the bandwidth we get on Ethernet. But if we take the same 1500 bytes, this curve here is InfiniBand, you see that we reach the maximum throughput on InfiniBand at much smaller packages than we do on Ethernet. Even though some of you might have heard of jumbo frames, which is 9000 bytes, we see that around here, we are still far away from actually utilizing the bandwidth. Then there's a special version of Ethernet called RoCE. That's for RDMA over converged Ethernet, where you can do RDMA on Ethernet, but only 3 cards in the world support that. We're not going to go too much into the deep because we don't have too much time in this session, but I mean, Ethernet tried to solve it with all kinds of things. Let's do offloading, let's do checksum, let's do chimney, let's do a lot of stuff. Some gained bandwidth but lost latency, some gained latency but then lost bandwidth, and some just didn't give anything in the real life. Whereas InfiniBand is a much smaller stack, it's all in silicon, so it's much leaner and much faster. To compare them, the fastest Ethernet switch in the world will switch packets at 2.3 microseconds. Compared to that, we see 0.1 microsecond on InfiniBand. And end-to-end, from one server over a NIC to the switch and over to the other and back, we see less than a microsecond on InfiniBand, whereas we are above 3 microseconds even on the fastest installations. And this is important because we want to use our storage differently. An old problem was that, you know, the InfiniBand cables used to be just 15 meters long, so we need them longer. And converting them to fiber, we would probably say, well, it will take time, but actually currently we do that in 550 picoseconds. I don't know if you know what a picosecond is, but it's a lot of zeros, milliseconds. So in a sense, converting it to laser light, moving it over large distances and converting it back is not an issue. It doesn't introduce latency. So why would we use file shares? Well, first of all, we have massively increased the stability. I mean, personally in my own lab, I've had an analysis services cube being built on top of 1.3 terabyte data warehouse. And I've been processing that, and when it's finished, I just started a new process, and when it was finished, I started a new. And I've been running that for 3 months, 24 hours a day, with no outage, with no network name no longer exists. Microsoft in their labs has done massive scale tests of this. It's really stable. Secondly, we have new functionality, I'll get into that. And then we decreased the complexity massively. If you remember that red drawing with all the boxes, all of that has gone away, because if we no longer have the storage directly on our SQL servers, but the only thing our SQL servers need to access is a file share, well, we get rid of the MPIO, we get rid of the DSMs, we get rid of the HBAs, the QDEPs, everything. We get a really simple solution. And usually the simple solutions are the ones that tend to run most stable. A requirement is that both ends, back-end file server and front-end SQL server, will be running SMB3, so that will mean the Win8 kernel are up, or Windows Blue. And another thing they did was, previous to Win8, when you did a clustered file share and you wanted to move from one physical server to the other, we would take the storage offline, take it online over here, and then re-enable the share. But that means for a few seconds, up to maybe half a minute, our file share would be offline. So if we had a SQL server up here, and actually everything we are talking about also works for Hyper-V, it can utilize the same storage infrastructure. But imagine your transaction log being placed on a file share here and it goes offline for 30 seconds. Well, SQL Server will not be happy about that. So you'll enter suspect mode and it'll be gray, and once you get it online again, it'll start to do a rollback and roll forward. And well, I have a client where the recovery process took 27 days. And I've never experienced that before. I even contacted some of the guys in Redmond, and they said, well, leave it. I basically wanted a copy and try to attach it without the transaction logging to see where we are. But they said, well, we haven't seen that. Please don't stop the recovery process. How long would you have waited? We waited the full 27 days, and it came online because the customer didn't have a backup.
Yeah, at some point you would have needed to do something.
Well, it was basically a make or break. So they said, well, we don't have a backup of the data. So if data is lost when this is finished, we don't have a company, because the backup system, 1.3 terabytes. It was actually so that they kept only 5 days of backup, and this happened on a Thursday. So Thursday the backup failed, and they started to look at it. Friday it failed, Saturday, Sunday, and Monday it failed. So on Tuesday they erased the first one because they didn't keep 5 backups that were succeeded. They kept 5 backups regardless if they were successful or not. So on Tuesday they no longer had a backup of the system. So they were pretty tense. But what the animation actually illustrated was that they have changed the code now. So when you do a clustered file share on Win8, you have an option of doing a traditional clustered file share or do a new high availability version. And if you do that continuous available file share, what happens is that instead of having the storage online on just one node, it will be online on all nodes. And on Win8 we can do 64 node clusters now. So we no longer need to take something offline and bring it online. We just need to tell basically the switch infrastructure which node handles that file share currently. And they can now switch that within the timeout of one TCP IP frame. So if I do transaction log process traffic from here to that file share and it's currently on node A, I can actually do unplanned failures. Go to the server room, unplug the power cord to this machine, and this one will resume that traffic without SQL Server ever noticing. So it's really resilient for failures. Then we have the multi-channel part, and it happens in many configurations. But what it was previously was that, like PCIe, like 1 lane, X4 lanes, X8 lanes, or like FDR, the Microsoft TCP stack just enable 1 lane, and there's a limit to how much traffic you can move on that 1 lane. And coincidentally, that was also pegged to a logical processor. And maybe you remember, at least I do, that we used to have servers running at 4.2 gigahertz, 4.4 gigahertz. Now when we buy a new server, they are 1.8, 2.0, 2.2. So servers or clock frequency is half what we used to be. But since they couldn't load balance one TCP stream, we could actually, with a 10 gigabit link, fully saturate one processor core. So that core would actually be our limiting factor and not our switch infrastructure. So what they did on Win8 kernel was that we could open multiple lanes, and all the lanes could be round robin across all our CPUs, so we'd no longer be bottlenecked on one CPU core. Another thing is that even though they now have teaming still requires maintenance and you need to set it up. They have what's called multi-channel. And multi-channel means that when the SMB client, let's say the SQL Server, contacts the file server, this guy says, hey, by the way, are you an SMB3 server? And says, yeah, I am. So he says, well, give me a list of all your NICs and all the capabilities, and it will return that up here, and this guy will realize, you know what? You have a NIC on a different subnet that I also can connect to. So let's, without any teaming configuration, let's use that bandwidth. So what it will actually do is open one lane here, second lane, third lane, fourth lane, fifth lane, sixth lane, and so on. And then if one of them falls out, it will move all those lanes within the timeout of the TCP packet to this one. So he will resume everything. Once this one goes back online, we will redistribute all the traffic, and we have a demo of that. The capability to do this requires RSS, receive-side scaling, but I think servers in the last 10 years has had that capability. So this is just to show that if you are not RSS capable on your NICs, but I'm pretty sure you are, it will only open one lane on each NIC. And the good thing about this is it's linearly scalable. So again, today in your existing SAN infrastructures, if you need more performance, you usually need to buy different components. But here you see running one NIC 1 gigabyte a second, 2 NICs, 2 gigabytes a second, 3 gigabytes a second, 4 gigabytes a second, and it just scales linearly whenever you put in something new. And this is on Ethernet. Imagine this was InfiniBand. It would be 6.8 gigabytes a second, 13 gigabytes a second, and so on, up to 26 gigabytes a second for just 4 ports. Then we have the RDMA part. Microsoft called that SMB Direct, but the interesting thing is that when an application needs to access something remotely, it goes to the SMB client. The SMB client figures out, well, the one I'm connecting to, he's also RDMA capable. So I'll reroute it away from the TCP IP stack in Windows to a special RDMA protocol, go over the network, bypass the entire operating system kernel over here, and go directly into a memory space. And the interesting thing about this is, well, we started talking about PCIe cards for flash memory. So I'll come back to a drawing about that. But if we do this, we have no latency overhead of accessing something in a different server. And just really quickly, what happens is that it starts a normal SMB traffic, port 445, but then it figures out, hey, you are RDMA, so let's move the traffic to something different that is really, really high performant. We don't touch the OS down here, but we keep this guy alive. I don't know if any of you have worked with ISDN back in the days, where you have like B channels and D channels, and you can more or less compare this to 2 data pipes, and then you have this control channel. And actually, if these guys for some reason stops working, it will move the traffic to traditional Ethernet. But all of this means we can do some new kinds of setups. So we can still do our SQL cluster, but then we'll put in a file server, and we'll put in all the PCIe flash cards like the Violin Memory cards, and then this SQL server up here can access that flash card in a remote server. But when we're using RDMA, we have absolutely no latency overhead of doing this. So all of a sudden we can do direct attached local storage that would normally be pasted in just one of the servers. We can put it in a file server, expose it as a file share, and we can actually build a SQL Server cluster on top of it, or a Hyper-V cluster for that matter. Then you might say, well, this guy, that's a single point of failure. But I would say most installations of SANs do not have redundant storage arrays anyway. And also, since on this guy we only have what's on the Windows CD and then a driver for this card, there's no MPIO, DSM, or no strange software. And also, we don't have SQL Server on the node. Because, I mean, I have SQL Server customers that had a SQL Server that became important. They clustered it to gain uptime, but now they gain more downtime because of whenever cluster manager has a problem and it sees it misses the heartbeat in the clustering, it might say there's something wrong with that node, stop SQL Server, move it to another node and start it. And you get all these false positives. So I actually have clients that have moved away from clustering back to a standalone server to get better uptime. But if you do a SQL Server and you can actually, like some of the other sessions here, you now have code and indexing strategy that puts your CPUs at 100%, that will miss the cluster heartbeat, and the cluster will stop that SQL Server and start it somewhere else, even though what you did was do really, really good SQL Server performance code. But now that the storage part is down here and we have SQL Server up here, we no longer have that problem. But if we do want redundant, well, then we have that continuous available file share we shared, where this guy, I can pull the plug on him and he can resume the activity. Of course, the requirement then becomes that all of the file shares up to 64 nodes will need to be able to access the same storage. And that's where the Violin Memory arrays fit in perfectly, because they connect either via PCI Express, they connect via fiber channel, iSCSI, InfiniBand, and so on. And to do an actual kind of drawing how we would do it, some SQL Server nodes, we would put in the MarkSUSE TempDB Fusion IO, Violin Memory, NAND flash cards. We'll have the InfiniBand infrastructure, we will have the clustered file servers, and then we'll have the Violin NAND flash array down here. And those links, I mean those two lines is 13 gigabytes a second, so we have massive bandwidth, and these guys are 3 point something gigabytes a second for most of them, so we can actually attach 4 of these before we saturate that, and that means if we need more, we'll just add 1 more card and we can add 4 more. So it's a platform that is really, really scalable, that even despite the growth you might have in the future, you can start where you are right now and very, very easily move that. One of my clients actually said it perfectly. He said, whenever we hit a performance plateau, we can't just add something and continue. We need to do a technology shift and install something new, do a migration and then run again. When we hit that bottleneck, we need to do a shift once again and do a reinstall. On a platform like this, all the components, we can just keep on adding because the infrastructure and the bandwidth is so massive. And really quickly, we have some demos of this, but we recorded them just to make sure that in the short time we have. But what we're doing, if it's playing, is over here you see logical disk. So this is a test on the server, the lower servers, the file servers that owns the Violin Memory array. I don't know if you know Iometer. Iometer is a really fantastic tool to do I/O testing because it's open source. Intel originally developed it but gave it away for free, and every vendor in the storage business accepts it. But we did some workers. We chose the Violin array. We've done. You need to put in the file size in sectors. And then the type of I/O we do is 64K sequential reads, which is what SQL Server spends most of its time doing. So that's a very relevant test. Yeah, because I was not sure I could see the cursor, so I just moved it back and forth so we can see what we did. But 100% read, and then we started, and what we'll see is that we run at just about 3 gigabytes a second. 64K IOs, 50,000 IOPS, and over here we see 1 millisecond latency, and we see it's 1.2. But remember, this is 64K IOs, so we need to divide that by 16 to get 4K IOs, which is what everybody measures in. So that's less than 100 microseconds for each I/O. So I think that's pretty well, and that's for local storage. Then if we move on, what happens in the next setup? You see I have the same performance counters, but for the ones that are really observant, you see it's no longer logical disk. It now says SMB client shares. But if you go to a Windows Server 28R2 and look at the SMB or networking performance counters, you need some sort of NASA degree to understand them, because they are completely insane. They make no sense at all. And they realize that and say, well, in the Win8 time frame and on, well, a file share is on par with a logical drive. So they basically cleaned up the counters and say, well, we have average bytes per read, per write, second for read, second for write, read bytes a second, and so on. So that you can, whether you have local storage or SMB storage, it really doesn't matter. We can measure it the same way. But down here we did the same thing, 64K sequential reads, same kind of workers, and you see the end drive is a file share, it's not a local drive. And if the one recording, which was me, would speed up a little bit, you will see that we will gain almost the same as we did. We did just about 3 gigabytes, here we do 2.7. But there's a reason for that, and that's the lab equipment we got access to. My lab is not that big and I don't have that investment. Are network cards that are not RDMA capable. Had this been RDMA capable network cards, we would see exactly the same. And even better, in some cases we would see more. And I thought when we were building the Windows 8 kernel and we did some testing, when I did local, I would see 3 gigabytes a second. When I did remote, I saw 3.4 gigabytes a second, which doesn't make sense. Here, I'm just going to show you in PowerShell that RDMA capable. This is my 2 InfiniBand cards, and you'll see that it says false, just to prove that when we are RDMA capable, we will see some different numbers. But the reason for this was that when we run it like this, we burst all the packages over the network and send them in big chunks, whereas locally NTFS doesn't do that. It just issues the IOs whenever they show up, and it turns out that's less effective than the network redirector, which came from 1 megabit and 10 megabit links, and they just kept that code that bunches it up and chunks it away. Another thing I'll try and do is to disable one of the NICs, just to show the failover part, that this guy here actually simulating SQL Server. You will see that all the traffic moves to one of the NICs and nothing on the other. And once we go over, I'll just skip a little bit in this video. If we're lucky, you'll see when I re-enable it here, you'll see that the multi-channel part figures that out, sees we are connected, and then if we are lucky, it should actually redistribute the traffic across the 2 once again, like this. So, and again, iometer is our SQL Server thing doing almost 3 gigabytes a second of traffic to a transaction log, and there's no outage. It never realized that something went out of service. And then just the last demo is to show a new technology that's really expanded in the Windows Blue, Windows Server 2012 R2. Is something called storage spaces. So now you see I only have one of these violin arrays, and what we're going to do here is, because find the mouse cursor, we'll combine them, but first we'll do some, this is just to show you that writes also work, as Jens said. So this is 100% sequential write test we do, and we should hopefully get the 2.6 gigabytes a second. Okay, just before it, so this is the storage spaces, where you can see we have our 2 physical drives here connected by a fiber channel, and then we combine that into one array here.
So that's on 2 different arrays, combining performance over 2 arrays.
Yeah, and if we take the properties, we'll go in and see that we have a mirror configuration to do, if we scroll down here, so we'll see that to do it high available, we could do one violin array in one data center and another violin array in a different data center. Then we do a mirror across and say, well, this is in software, that must give massive amounts of overhead, but once we start this test, you'll see that, well, we run with exactly the same performance, there's no overhead whatsoever, and we also do tiering and caching and all kinds of stuff. But the really interesting thing comes when we start to do reads. So I'll yes, we're writing right now, but what you'll see in just a second, we'll reconfigure iometer to do reads here, 100% reads, and something magic happens, because since we know that we have everything on both arrays, we can read the first chunk on one array and the second chunk on the second array and so on. So we actually get the doubled bandwidth. So now we run at almost 5 gigabytes a second on a mirror, which is normally not possible. So quickly going on, virtualization, that's also happened a lot in there. But typically we didn't have the I/O when we virtualized SQL Server, and everybody wants to virtualize. We have solved all the stuff about CPUs and number of cores, but Hyper-V version 3 and also Windows Blue had these things of being, of course, adopt new technologies, but also be the best hypervisor for SQL Server. And that basically means being able to handle high I/O loads. Some statistics that Microsoft used was that, well, 4 is enough based on all the Windows servers, but when you zoomed in on the SQL servers, you saw that it's a very different distribution. So we worked with them. I will not go, these are in the slides, just examples of how you would consolidate. The Hyper-V team had a very strange idea of how to consolidate. But it ended up with supporting 320 logical processors, 64 in each virtual machine, and 1 terabyte of memory. So we just needed to solve the I/O, and when they released Win 8, VMware just came out with 300,000 IOPS, but Microsoft did it with 985,000, almost a million IOPS from one virtual machine. And I'm guessing most of you can run on 64 processors, a terabyte of memory, and a million IOPS. So we would do something like this, and putting Hyper-V in here means that since normal Windows clustering is just shared disk, if I want to move from one node to another, I need to stop, move, start, and do rollback and all that stuff. But Hyper-V, like VMware, can do in-memory clustering. So I can move a running SQL Server from one physical node to another physical node without ever disconnecting clients. So you can get massive amounts of high availability. And just really, really quickly about the Windows Blue, because I think we're over time. So Windows Server was RTM back in September. Some of the new stuff was that Hyper-V went to 1.3 million IOPS on the same hardware from a virtual machine. The reason for that was that they improved the virtual NIC performance from 300,000 IOPS on one NIC to 450,000 IOPS on one NIC. And we have that improved storage spaces you just saw. And I have my first client. We actually moved to Windows Server 2012 R2 from 2012. It's an in-place upgrade. You don't need to reinstall your machines. And doing 8K IOs like transaction log, we went from 950 megabytes a second on a NAND flash card from a vendor I'll not mention in this seminar to 1.3 gigabytes a second. Same server, same hardware, same investment, just the new Windows kernel. Massive improvement. SQL Server still in development. I think they're saying around February. This is the last thing I heard. We now have an in-memory OLTP, which is basically hotspot tables for ERP systems or stuff like that. We have the updatable column store indexes. Always on has been improved. We can now have 8 replicas. We can even have replica in Azure. Improvements for scalability. I don't know if you know, they don't publish it very much, but there's a completely new query engine in SQL 14. It's not enabled by default when you migrate databases. It's only enabled when you create new databases or you move the compatibility level. So you need to be aware of that. And actually in SQL Server 2012, back to 2005, I don't know if you're aware of trace flag for 4199. So 4199 enables all the new engine features that they have been doing. So like some of you probably know Connor Cunningham, which runs the SQL Server optimizer team. When they do something really brilliant that breaks how SQL Server acts, they couldn't enable it by default. So some of those features are not in SQL Server 2005, 8, 8R2 or 12. They are in trace flag 4199. But on SQL Server 2012 R2, or no, that's not what it's called now, SQL Server 2014, the new engine is there, and by default on new databases, but you need to change compatibility level on databases that you attach from older versions. Now we can actually manage, so in Resource Governor we could manage CPU and memory allocation, but as Jens just showed you, and I'm guessing most of you have that experience, your CPUs are at 13, 12, 8% while you wait on storage. So on earth would I need a Resource Governor policy to control a CPU that's never above 20? So in SQL 14 we can now control IOPS, because that's the limiting part of our systems. Then we have something called buffer pool extensions, and really quickly about that is that because of systems like Violin Memory, we are now so fast on NAND flash storage that we are almost on memory speeds. So if we traditionally look at NAND flash as a storage component and not a memory component, well, we started thinking maybe we should think about NAND flash as a memory part. So like we have level 1, 2 and 3 caches, maybe DRAM would be level 4 and NAND would be level 5. So what you see in SQL Server 14 is actually level 1 memory and level 2 memory. Now we can extend the memory of a server where you might not have more DIMM sockets, or you don't have the budget to buy more memory. You can plug in a NAND flash card to the buffer pool, and the buffer pool manager, if it will change slides, so will now be the normal DRAM will be our level 1 buffer pool. We will put in PCIe flash cards, which will work as a level 2 buffer pool. And as some of you might know, every single part of SQL Server, none of them can access storage. It's only the buffer pool manager. So it's pretty easy for Microsoft to say, well, if it's not in the data cache, the buffer manager will fetch it and put it in and give it an address. Well, now what it does is it will read much more into the PCIe flash, and if it's not here, it will just put it up there. None of the other parts of SQL Server needed to be rewritten to do this. Very, very easy to enable. And I'm sure you'll get the slides. Oh, and now it says PowerPoint stopped working. Fantastic. This is actually a Windows Blue machine I'm running on within. Somehow the Office team didn't test very well on Windows Blue. Integrated to everything, performance monitor, X events and so on. And then on the hardware side.
Then you can take that. You know.
Okay, but Jens explained the Violin Memory box, but inside of it there's two gateways that actually controls everything. They run embedded Linux, but now the new thing is that they run Windows Server inside of the Violin array. So now we can even take away the server part of our drawing from before. So we just have a Violin array with Windows 2012 R2 internally, exposing SMB3 file shares directly to our SQL servers. So again, massively decrease the complexity of an installation like this.
That would be like an NOS device.
Yes.
Yeah.
But running at extreme performance.
And something between.
Early access now and general availability is in January. And every management will be part of standard Windows management tools. So no special storage tools needed to manage this.
Yeah. Sorry for going over time, but big subject, lots of information, so I hope you enjoyed it. And
thanks for coming.
yeah.